Hello, my name is Nikolai Karpov, and I'm going to present joint work with Jim Drunk on the tree similarity drawings. Okay, so basically let's start with the definition of the problem. Yeah, in a tree similarity drawing, we are given a set of trees and some threshold k, and we need to output all pairs of trees such that the distance between these trees is at most k. And by the distance, I mean the tree added distance between trees. And for this talk, we just assume that our trees are rooted, ordered, so basically the fix of a children matters, and each node has a label on this node. So the tree added distance is a minimum number of insertions, deletions, and renaming of nodes, such that by using these operations, we can convert the first tree to the second tree. So let's speak a little bit more about this. Just, for example, we have a tree on the 5 nodes, and we can remove some node C. Then we just join all children of node C to the parent of the node C with preserving the order. Okay, so the next operation is just rename of a node to not a node. So basically, we can rename a node A, node F, and we can obtain the same tree, just with one exception, that the root has a name F, not A. Yeah, and the last operation is the insertion operation. So basically, we can insert node in an arbitrary place. Yeah, for example, on the picture, we just insert node with the label G to the tree as the children of A between children B and children C. Okay. Okay, let's speak a little bit more about why we are studying this tree similarity drawing problem. Yeah, in the modern world, tree appears everywhere in our data, and a lot of data is the structure of tree. For example, some popular formats like XML or JSON has a tree structures. Also, just if we consider the program, we can organize this program as an abstract syntax tree in any programming languages. And basically, if we're doing some refactoring, some operation on a code, it's also useful to use trees instead of just tree set of strings. Yeah, also, we can use tree for natural language processing and for some bioinformatics tasks like a tumor research. Yeah, so basically, yeah. And if we are doing some clustering and classification on trees, basically the tree similarity drawing is a fundamental task for these applications. And basically, it's the reason why we are trying to study this problem. Yeah, and just for example, how we can convert simple JSON into the tree. For example, on a JSON, you have a the JSON contains 3 books, properly Rorschach and Jane Austen, and basically it is a way, the natural way how we can represent this JSON as a tree data structure. Okay, so let's speak about previous work on this problem. So we have a pretty long line of research from Sigma 2002, and so Tang and Hatter. So basically, most of this work follows the following framework. And we call this framework like filter then verify framework. So basically, on the first stage, we just extract some superset of the real answer. And after that, we just run the verification procedure to compute the distance between candidates by using some exact algorithms. Yeah. And usually, step one is sequential, but step two can be parallelized because we can check each pair of candidates independently. Okay. So let's speak a little bit more about filtering step. So usually, the filtering works in the following way. At first, we just convert tree into some simple objects like string, sets, or set of integers. Yeah, and after that, we pick some distance on transformed objects, like Euclidean distance if it's the vectors L1, yeah, string distance if it's strings, or Jacquard similarity distance if it's the sets. And after that, we use the distance on transformed objects as a lower bound for the tree-added distance. And by using these lower bounds, we just prune the candidates. So typically, this lower bound is more efficient to compute than tree-added distance. Yeah, for example, the tree-added distance has a cubic prime, and you can compute the distance in a square time or equivalent distance in a linear time. However, there is some disadvantages to this approach. The first disadvantage is really hard to obtain some good approximation for the tree-added distance as a lower bound. Yeah, the second, such transformations, when we just map tree into string sets, we lose some tree structure that basically is essential. Sometimes it's very essential for computing the distance. Yeah. So let's focus a little bit more about some specific algorithms. For example, Anketo, they use a partition-based approach. They just split tree into small subtrees, and after that they construct index on this collection of subtrees, and basically try to output candidates that have a common subtrees. Yeah, and for the proving the correctness, if we pick subtrees, it's pretty small, and construct some consistent way how we can extract these subtrees from the original tree, we can prove the correctness, we will output the whole set of candidates. Yeah, however, one of the limitations of this work, this indexing procedure is pretty sequential, and as far as we know, it doesn't scale for large thresholds. So basically, when we pick a large threshold k, then these three subtrees became so small that we have so many matches, and basically the set of candidates for checking the exact distance is extremely large. Okay. So another work which basically achieves the state-of-the-art result, it follows to the filters and verify framework. Yeah, and basically it uses some embeddings and a lot of embeddings, a lot of lower bounds. They compute some index, the data index dynamically, and after that they use some efficient verification scheme when they combine upper bounds and lower bounds, and yeah, and thus compute the exact answer by proving a lot of candidates during the exact computation distance step. So, however, this approach also has some limitations, and the main limitation is the lack of parallel a lack of parallelism. So basically, this dynamic building index procedure is pretty sequential and it's hard to parallelize it. Okay, let's move to our approach. So basically, our approach contains three steps. At first, for each tree, we generate some set of signatures. After that, we generate candidates who share these signatures. And after that, we verify the candidates by using the detect algorithm. Yeah. And the main advantage of our algorithm is that basically we don't use any numeric indexing or hard indexing step. So our algorithm is scalable when you consider multi-core or parallel combination environments, or maybe even MapReduce. And additionally, in our experiment, we show that it works extremely well for large values of k. It scales perfectly when the value of k is comparable to the size of the trees. Okay, so let's speak a little bit more about signatures. So signature is a sum function that output a small set of integers by using p and some sequence of random bits. So basically, the key property of the signature is the following. So if the distance between trees are small or less than k, then the probability that the set of signature has an intersection for trees is large. Yeah, so by using this property, if we just fix the randomness, generate set of signature for each tree independently, after that we can use some hash table to make a triangle house signature and produce a set of candidates for the exact computation. Yeah, so basically the key contribution for work is introducing signature-based joint framework. Also, we propose two signature generation schemes, which we call Paul signature and Eller signature. Also, I would like to note that the proof that the signature works is pretty untrivial, and we use some nice analysis to prove the correctness of our algorithm. And in our experimental section, we show that the new algorithm beats outperforms the state-of-the-art approach, even on a single core. But additionally, our algorithm is fully realizable and you can implement it in distributed fashion. Yeah, so let me talk a little bit more about the experiments. So, for example, T-join basically is the result of the algorithm from the Hurter and al. And which is corresponds to a blue line on the figures. And Bitjoin is both signature from our paper, and eJoin is Eller signature from our paper. So basically, we tested it on two data sets for the code analysis and one data set for one genomic data set. And as you can see, just our algorithm works extremely well when the size of a tree are large, and it significantly outperforms the previous approach. Yeah, and this is just to figure how our algorithm scales when we increase the number of cores. So as you can see, compared to the T-join, which is pretty sequential, and only the last step can be implemented as a parallel, our algorithm scales in all parts, and basically it significantly outperforms the previous approaches. Okay, so basically this is just a short summary. Yeah, we introduced two algorithms, we introduced the signature-based work, And one of the directions, future direction, is a new signatures here, maybe for trees, or maybe for graphs, or maybe for another options. So, thank you very much.